our new climate change program, and she has a couple of announcements.
Yeah, thanks. I just wanted to let everyone know about the University of Montana's new Climate Change Studies program that was developed by a group of faculty over the last 2 years under the guidance of our provost, Royce Engstrom, who's in the audience here. A lot of great leadership to see this happen. We're actually one of the first universities in the nation to develop a program like this that offers students a minor in climate change studies. And the way we've developed it is that students get a multidisciplinary understanding of this issue. So we have them take coursework in the science of climate change to help them understand the Earth's climate system and humans' influence in that, as well as coursework that helps them understand what this means for us as a society and what we might do about it. And so students take an introductory course and then coursework in 3 different areas: in the science of climate change in society, and then climate change and solutions. And in the solutions part, we get students involved in internships and practicums and working actively to try to address climate change. So it's open to students from across the campus. We're trying to recruit students from different departments. We've had students interested from psychology and wildlife biology, environmental studies. So it's a great group of students bringing their expertise to this course of study. As well, for the community, we've been trying to offer lectures and opportunities for us to get our heads wrapped around this issue. We had a lecture 2 weeks ago. Someone came in and talked about the connections to national security. Here's our kind of plan B, talking about geoengineering as well. Scott Mills will be talking next week about the implications for wildlife. You'll see on one of these slides. And David Orr is coming in with a President's Lecture Series to talk about the climate crisis. And he's an incredibly engaging speaker too. So hopefully there's opportunities for the community as well as for students. There's a website that tells people about the different coursework. So there's students here, get in touch with me, or look at the website for other opportunities for community members. Thanks.
If you see a blue clipboard coming around, that is our sign up if you want to get emails from the Center for Ethics for events like this. So if you put your email address down there, we'll let you know when we have these kind of events. So I think you're in for a real treat. David Keith is a tremendous science communicator. And this afternoon, I think he's the kind of guy who really kind of picks out what are the very important things to think about and articulates them in an extremely clear way. He's very accomplished, and we're very fortunate that he has this connection here to Missoula so that we can bring him down here to give this talk. David is the director of the ISEE Energy and Environmental System Group. He's the Canadian Research Chair in Energy and the Environment. He's in the Department of Chemical and Petroleum Engineering and Department of Economics at the University of Calgary. Professor Keith has worked near the interface between climate science, energy technology, and public policy for 20 years, despite how young he is. His work in technology and policy assessment is centered on the capture and storage of CO2, the technology and implications of global climate engineering and economics, and climate impacts of large-scale wind power and prospects for hydrogen fuel. He now leads a team of engineers developing technology to capture CO2 from ambient air at an industrial scale. He's both accomplished in communicating to the public and writing in the most prestigious science journals, and he also was listed as one of Time Magazine's Hero of the Environment in 2009, and I believe there was a quote from Bill Gates, bringing some prominence to these issues that he's trying to bring to public attention, and was named Environmental Scientist of the Year by the Canadian Geographic in 2006. So let's welcome David Keith.
Thank you very much. If you can't hear me at the back of the room, put your hands up or wave or something. I'm going to start by really, this talk's going to be, I'd say, in 3 pieces. So first, I'll give you some background about how I happen to think about the climate problem. And I know you probably, a lot of you heard about it before in different ways, but I hope to say it in a way that's a little bit new. Then I'll say a little bit about how that connects to another energy-related problem, which is whether or not we're going to run out of oil and how those 2 problems connect. And then I'll get to the sort of core of what this talk was advertised to be about, which is about whether or not it makes sense to think about engineering our way out of this problem in ways other than the normal way we think about, which is just to cut emissions. So you've all seen pictures that look something like this before of smokestacks belching smoke. And I want you to think about this in a way that's a little more quantitative. So what these things are doing, what we're doing when we get all this fossil energy, is we're transferring fossil carbon, carbon that is 100 million years old. We're transferring it to the active biosphere. And there's a flux of carbon as we dig it out of the oil sands or the coal fields or pump it out of the ground. There's a flux of carbon that we've engineered, not because we want to change the climate, but because we like all the wonderful things that energy brings us, like illumination and mobility and computation and so on. But we're engineering this huge flux of carbon from the underground to the atmosphere. And it's easy when you look at these to think, well, is this just a local problem or not? And the atmosphere is a pretty big place. What's the comparison between this flux and and nature? And the answer is that we are completely overwhelming nature. So the flux of carbon from deep underground to the atmosphere, there is a natural flux. And that's what happens in, say, volcanoes, which you see on the left. So volcanoes are taking ancient carbon from underground and putting it in the atmosphere. And there are a bunch of other these, there are seeps where fossil fuels leak to the surface. That's how we originally used to find fossil, say, oil. We found it when it seeped to the surface. And those things end up being CO2 in the atmosphere. And the rate at which we are now transferring deep underground carbon to active biospheric carbon is, that number is uncertain by quite a bit. But let's say between about 20 and 30 and 100 times faster than the natural background rate. It's an extraordinary sort of geophysical event on the planet. And there's a tendency to think still of ourselves as being a relatively small perturbation, a small change on top of the underlying sort of vast scale of nature. And I think this number really drives home the extent to which on this topic that is absolutely not true. We are completely overwhelming any natural cycle at this scale. If we kept doing this for a long time, we would have a completely different climate than the climate we have now. The only questions are about how long that time is and what that different climate looks like. But this is a sort of geological, geophysical force on the planet. You may be wondering, some of you may have thought of different comparisons. You can compare the annual flux of CO2 from fossil fuel burning to the annual flux in and out of plants. And when you do that, we look like a small perturbation. We're only maybe 10%. But that's the wrong comparison, because the plants in the northern hemisphere, they grow in the summer, they take CO2 out of the atmosphere, and then when they rot, they let it back out. That's an annual cycle. What we're doing is not an annual cycle. We're transferring ancient carbon back to the active biosphere at a rate that just overwhelms what nature does. And we're doing that into a very thin atmosphere, not very much total mass. This is the atmosphere as seen from the space shuttle, where you can really see the upper thin part of the atmosphere that is where a lot of the action happens that regulates the climate we have. We don't know exactly what's going to happen when we change the amount of carbon dioxide in the air. So the numbers we tend to measure this in are parts per million in the atmosphere. In the last 10,000 years or so, during what we call the Holocene, during the time we've had no glaciations and the time that our civilization has got going, we've had, say, 270, 280 parts per million. We are now increasing that pretty rapidly, and it's now 380, and it's going up. And left unchecked, we'd easily get to something like 1,000 by the end of this century if we didn't do anything about it. And we have lots of fancy computer models and very simple models. If this problem all depended on fancy computer models, you'd be right to be skeptical, but that's not the basis of our knowledge. But in some ways, the basis of our knowledge is to look back in ancient history. So 55 million years ago, roughly, in the Paleocene-Eocene thermal maximum, we had a couple thousand ppm CO2 in the air. So this is walking backwards in time 50 million years. You can see, I mean, we don't know this precisely, but there's no doubt about the basic facts that we had several thousand, that's this y-axis here, parts per million of CO2 in the air. And it took something like 10 million years for the CO2 concentrations to drop. And during the time we had that much CO2 in the air, we had alligators in the high Arctic. It's a completely different climate than what we had now, an equitable climate. And by the way, if you put that much CO2 in a current climate model, you don't get a climate that supports alligators in the high Arctic. So there are feedbacks in the system we don't understand. that made this equitable climate that we used to have. And there's nothing bad or good about that climate. So a comment you often get about climate change is, essentially it's all natural, why should we worry? So if our civilization and our crops and the locations of our cities on coastlines had evolved in a climate like that, that'd be no problem. The issue is about the speed of the transition. There's nothing intrinsically better about this world than that world. But we are going to take the CO2 concentrations back to what they were in that world in my children's lifetime. That's the pace. Okay? 100 years from now, we'll be up at 1,000 ppm if we don't stop. That's 100,000 times faster than the rate at which the CO2 concentrations decline. This is extraordinary fast thing on geophysical timescale. That is not a statement that we'll get back to the same climate. We won't. But it gives you a sense of how hard we're pushing it. We're not some little force on the planet. It's enormous change at the scale of the sort of core processes that keep the climate going. And I think it's important to keep coming back to evidence like that, because this is stuff that is not captured well in climate models. We're learning more about it. And it gives you a sense of just the deep uncertainty. We really don't know exactly what's going to happen. And the issue isn't about whether it's better or worse to have this changed climate than the current climate. The issue is about the fact that the kind of crops we grow, the locations of our cities on coastlines, all these things have been adjusted to this climate. And changing that fast is really going to be dramatic. So we've known about this for a long time. Arrhenius calculated how much the climate would change if we doubled CO2 in the 1890s. And he got roughly the same number we get now. He spent a long time doing it. He actually did this calculation that I get my students to reproduce in Excel. And I think he was going through a divorce at the time, and he decided to do these latitude by latitude calculations by hand, presumably because he needed to take his mind off it. But he got exactly the same number that we get now. Couple degrees C, global average change for a doubling of CO2. So the idea that this is some new thing that we just learned from fancy climate models is wrong. Basically, as soon as Tyndall had taken adequate measurements of the fact that CO2 was a radioactive gas, and Arrhenius had those, that absorption coefficient, they were able to make the first calculations of what might happen. This is a newspaper article from the New York Times that says pretty much what all the newspaper articles from the New York Times say today about how the climate's going to change and how industry is going to change it, except that it's from 1953. And this is, I just show this to illustrate the fact that this is not new knowledge. And the reason I think this is important is I think we're, in this kind of internet-driven society, you keep seeing a new paper or a new claim that says A or B, and you can easily think that things are changing really fast. And yet I've now been 20 years working on the climate problem, and in many ways, a lot of the core science hasn't changed at all. And this report, I mean, this article came out long before, 10 years before I was born, and that was the beginning of this core science, and yet we've done essentially nothing about it. So just giving you a sense of different timescales. Now I'll say two things give you a sense about the momentum of the problem, and then I'll take a pause. This is time on the bottom and amount of CO2 emissions measured in billions of tons of carbon. And this is the actual historical emissions. And I've left the last 2 years out. The next 2 years went higher, and of course this year with the recession is going to be lower again. And an interesting thing is there have been these projections by the IPCC, UN Black Helicopter Group, to try and tell us what it's going to look like in the future. I'm a member of the IPCC writing team at some point. And this is where we need to head if we want a stable climate. And this is where this is what IPCC said was the highest emissions would likely be. And in fact, we're over that trend. Now, this isn't a bad thing. What you're seeing there is partly the fact that 100 million people in China have got themselves out of poverty and have been building coal plants at a rate that is just hard to believe. And it's surely not a bad thing that people have access to some of the things we all like here, but the consequences of it are going to be big. This is another thing that's concerning, and it's the melting of the Arctic ice. So this is the change in summertime Arctic ice cover over time. And this is a bunch of model projections. And there's no question from the models that we expect if we keep putting CO2 in the air, all the Arctic ice will go away in the summertime. But what's been happening is that the actual data shows a much faster decline than the models predicted. And that may be partly a fluctuation. The last 2 years haven't been as bad as the trend. But it's a sign that we don't understand the system very well, and that if we push the system hard, we should expect to be surprised. So this is, I don't mean to knock wind power, because wind power is one of the major energy sources we could build at scale, but this is a sort of summary of what we've been doing about this problem so far. And I don't mean to be mean, but it's extraordinary, the ratio of talk to action. There is an amazing, among the kind of elite political class, an amazing talk about the idea that we're going to do something about this problem, and the actual actions are almost all symbolic. So it's very nice to put solar panels on fancy architected buildings, but it does essentially nothing about the problem. We have to change the heavy basics of the energy system. And we have to do it in a way that's relatively cheap, or we're not going to be able to afford it. And if you went around with a kind of meter and came down from Mars and said, can you see any evidence humanity is actually investing in the changes in the energy system necessary to really pull emissions down, you'd have to say no. The best single evidence of this is that Europeans, who at least in perception of North Americans and in the Europeans' own minds seem to be the leaders on climate change, they're building quite a number right now of uncontrolled coal-fired power plants, which is the single thing you would actually not do if you cared about the problem. So it is just political nonsense to say we're going to pass some laws or have some carbon trading scheme or invest in a lot of solar PV in Germany if you're still building coal-fired power plants. It's a fundamental sign of a disconnect between happy talk and actual reality, which is that we're doing almost nothing. So we could stop. So I'm not saying that we couldn't stop. I'm saying that we aren't stopping. And those are really different. So electricity is the place you'd probably start if you really wanted to cut emissions, for a number of reasons. It's probably the cheapest place to squeeze emissions out of. The users of electricity are pretty decoupled, other than price, from how you make it. Most of you probably don't even know where the power comes from that turns your lights on. And so you can mix and match solutions. So whether you want to do large-scale wind power, which alone doesn't work, but with a lot of long-distance transmission and backup can do quite a lot, or you want to do nuclear power or coal with capture and storage or central station thermal, these are all things you could do at costs that aren't a joke. Solar PV is more or less a joke right now, but it's the thing you see on all the posters. But these are things that you could do today at huge scale, at gigawatt scale, and you could mix and match them, and you could actually decarbonize the electric power sector. Is this expensive or not? Well, it's billions and billions of dollars, but you have to put this in some perspective. The energy business seems like a huge business, but the raw cost of energy into developed countries is only a few percent of GDP. 5, less than 10, depends on exactly how you measure it. We can afford to pay more for energy and not have the economy go under. Here's some ways to think about the comparison. So economists try and estimate the total costs, not the benefits, but the costs of all environmental controls. Not the costs of the environmental regulators, but the costs of compliance. That is the cost of putting scrubbers on smokestacks, the cost of putting catalytic converters on cars. And those costs are estimated to be a couple percent of GDP in the rich countries. And my view is we actually got a really good deal for that couple percent of GDP. There have been estimates for the US Clean Air Act that the ratio of benefits in terms of the number of people who didn't die from air pollution, that the benefits exceed the cost by as much as a factor of 10. So I think we've done pretty well, but that's the cost. And the cost of dealing with a climate problem is about as big, in that sense, the cost of dealing with all other environmental problems. A few percent of GDP is a typical number. And is that big or is that small? Well, it's a lot more than we're spending now. It's about the same as we spend on the military, a lot less than we spent on the military during the peak of the Cold War. It's much less than we spend on healthcare or education. A couple of years of GDP growth. Here's a way to say it. There are serious estimates, New England Journal of Medicine, that the transaction costs in the US healthcare system amount to several hundred, 300 and some billion a year. If you gave me $300 billion a year and I had the freedom to do whatever was most cost effective with no political constraints or political correctness constraints to decarbonize the US electric power sector, I think I could do it in about 20 or 30 years. And I think, I mean, I've had this conversation with utility executives who run the plants, and they would agree with that kind of number. With that kind of number, you could afford to basically rebuild the electric power system with emissions-free electricity on time scale about 20 or 30 years at essentially zero emissions. So I'm going to say a bunch of things about what we should do or what we might do to deal with the climate problem other than cutting emissions. And I said a bunch of depressing stuff at the beginning about how we're not doing anything. But I think it's really important to say that we could. This is a social choice. And however we've done it, we made a collective choice to completely ignore this problem, other than talking about it a lot. So I just want to have a brief interlude, since this problem is really an energy problem. Though, of course, my talk's going to be about non-energy solutions, ways you manage the problem by just blocking out sunlight is the core of my talk. But I want to say a little about the other energy problems, because I want to give you some framing for how you might think about this problem compared to other energy problems. So some people have a view that we're going to run out of energy, and I am mystified about how any rational person thinks that. There are lots of interesting scarcities on this planet, like scarcities of land, or scarcity of atmosphere to dump our waste in, but there is no interesting scarcity of energy that anybody who seems to study it in a quantitative way finds. There is a scarcity of easy oil. And there's the problem that a lot of the remaining easy oil is in a limited set of countries that have a lot of problems. So we are going to run out of easy oil, but that is not the same thing as running out of energy or even running out of fossil energy. So let's have a little history here. 1859 is when Drake went and discovered oil. And he didn't just discover it by chance. There was already a pretty organized group of financiers in New York who'd figured out how they could use this oil to make compete with coal oil. And they funded him to go drill in a seep. I mentioned seeps before, and just that reason, he drilled and found oil. The Chinese had actually figured out how to drill for natural gas many hundreds of years before, and drilled much deeper than Drake, but this happened to be where it started. And it really started with a bang. We went from this one well to devastated hillsides covered with wells in just a few years. It was really something. And this ignited the global, in many ways, it ignited modern industrial civilization, which many bits of which had existed before, but it wasn't energized before. Sort of the intellectual and technical abilities that sort of are the hallmark of modern civilization were there before 1859, but not access to that kind of movable energy. And it was really that helped to ignite the population boom and the sort of technical boom we've seen around the planet. And oil was central because oil energized transportation. We are going to run out of easy oil. This is what oil prices look like since 1859. It's a really interesting story because we see this big volatility of prices in the 1860s, 1870s. And then, and this is kind of stunning, while oil demand and supply went up enormously, just enormously, from before 1900 to 1973, prices were basically always the same in constant dollars, which is a stunning thing. And then we've seen this huge volatility since 1973. And I don't think we're going to run into any immediate peak oil, but we are going to run out of easy oil. But that is not the same as running out of fossil fuels. We have enough coal in reach of the growing access of our sort of our technical eager beavers who can take it out of the ground. We have enough coal to supply our civilization at twice the current burn rate for many hundreds of years. If we burn all that coal, we will put enough CO2 in the atmosphere to turn this planet into something more like Venus than here. There is no interesting shortage of fossil fuels when it comes to CO2. We're not going to stop burning fossil fuels because we run out of them, any more than we stopped having stones. The Stone Age didn't end because we ran out of stones. We're going to stop for some other reason, one of which may be that we don't want to put too much CO2 in the air. And there are lots of ways you may be thinking, well, coal is good, but it won't turn my car. Yes, coal will turn your car because you can do coal to liquids. You can make an industrial process that turns coal into liquids. And this is something that is absolutely doable at oil prices like we're seeing today. And this isn't mystery at all. This is how the Germans ran a bunch of their military machine during the war. So that's, I think, all well, maybe I'll just show one last bit of a slide there. Just to give you a sense that I don't think that energy scarcity is a very interesting problem in the way that climate change is a problem. There's a whole bunch of things you could do. If all your problem was, was oil scarcity. You basically could do massive coal to liquids. The problem is they have huge CO2 emissions. But you could do massive coal to liquids. You could do a bunch of other things. I won't say much more. The costs are sort of similar to the climate problem. But the difference is this stuff gets done automatically. Because as energy prices rise, I don't want to overdo the magic of the markets, but clearly, as energy prices rise, it's in each person's interest, either as individuals or as nation states, to figure out how to get oil substitutes. And so to some extent, it's just going to happen. That's not true of climate change. Climate change is a global problem. It's a global commons problem. And it is not in such a simple way to each person's interest to figure out how to solve it. That's why we've had so much trouble solving it. So I'm going to change topics after that kind of broad introduction and come at another way to frame the particular reason why the climate problem is such a dangerous problem, separate from the reason of why we haven't made any progress. So the first thing to say is that the amount of climate change we get for a given amount of CO2 emissions, emissions is the amount of CO2 we put in the atmosphere each year, concentrations is the amount of CO2 that's in the atmosphere. The amount of climate change we get for a given amount of emissions is very uncertain. Uncertain at the levels of factor of 2 or 3 or more. This isn't the uncertainty that the climate skeptics have, which is their certainty that there's no problem. This is just the real uncertainty of the climate science world. We just don't know. And the uncertainty is big. It's the difference between there being not much of a problem and being a problem. So the MIT Center has thought about this as a roulette wheel that we're going to spin. And we could be lucky. And we could end up in the sort of little blue zone there, or the 3 to 4 degrees sea change, where we don't have all that much climate change. And climate change is not like some other pollution where everybody loses. Right? If you think about the negotiations about lead and gasoline, there were arguments about the cost effectiveness of pulling lead out of gasoline. But nobody benefited from having lead in their kids' brains. Right? Everybody agrees that having lead in your kids' brains is a bad thing. The debate was just about how much it was worth to cut it, how quickly. That's not true of changing the climate. That's one of the reasons this problem is harder. Well, I think there's no question that if the roulette wheel comes up on the bad side, overall, we've got a lot of losers. There will still be some winners. Because climate isn't a one-dimensional thing. There are winners and losers. In any case, we're going to spin this dial, and there's enormous uncertainty. And we could end up with global changes over 6 or 7 degrees centigrade, which is stunning. I mean, this is going to start to melt the big ice sheets quickly. It's going to make it hard to grow the kind of crops we have now. It's really going to be a big change. Or we could get a small number. This is what they have if we have business as usual, as we emit the amount of carbon that we're emitting now and just keep ramping it up. This is what they think happens under some particular scenario where we cut emissions. And this is a lot better. There's a lot more of the blue color. But the point is, even when you spin this roulette wheel, there's some chance of getting very dramatic climate change because of this uncertainty in how much change you get for a given amount of CO2 in the air. And that uncertainty is called the uncertainty about climate sensitivity, and it's central to the problem. And it often gets lost. You'll hear, if you pay attention to climate politics, you hear talk about aiming for a particular amount of CO2 in the air, like the idea that we're going to stop at 450 or 550 parts per million CO2 in the air. But it's not clear that's the right target, because we don't know how much climate change we get for that. It's quite possible that at 450 or 550, we have an unacceptably huge amount of climate change. And it's also possible it's not so bad. We don't know. And we're not going to know until after we put the CO2 in the air. So that's a statement about uncertainty. Separately, I want to talk to you about inertia. The climate problem is a stock and flow problem. It's like filling a bathtub. It's a problem that doesn't reverse itself quickly. A simple way to think about this, and this isn't anything about nuclear power being a good or bad thing. This is just to think about timescales. A lot of you have in your mind the idea that nuclear waste is this incredibly long-lived thing, and it is in many ways. But by some measures, in many ways the right measures, the impact of putting CO2 in the atmosphere lasts longer than the radioactivity of nuclear waste lasts. This is more or less a one-way valve. We put CO2 in the air, and the climate impacts of it extend out for tens of thousands of years. So one way to say it is if you ramp up emissions quickly and then stop suddenly, ramp up emissions exponentially and stop suddenly, which is, to caricature what we're talking about doing, the amount of climate change you get say 10,000 years after the day you stop emitting is about a quarter of much as what you got the day you stopped emitting. It's a very long-lived, it's not a pollutant if you like, it's a natural part of the ecosystem, but it's a very long-lived footprint on the Earth that we're making. And that inertia means that you cannot just wait to find out how bad the problem is to figure out what you're going to do about it. It's a fundamental part of the problem. Let me say something about how different that is. Well, let me say this. Let's say we decide to have some policy. Instead of talking about it, let's say we decide to really do something about it. We put in an even-handed carbon tax with income recycling. Income recycling means you take the carbon tax money and use it to cut income taxes so you're revenue neutral. Income tax is a tax on working. We don't want taxes on working. We want taxes on bad things like emitting carbon. So that's what you do if you actually want to be economically efficient and solve the problem. And then what we're going to do is replace some low emissions infrastructure, some high emissions infrastructure rather, the infrastructure we have, with some expensive, long-lived, low emissions infrastructure. And the purpose of that carbon tax, or whatever policy it is to get industry and all of us individually to exchange our high emissions infrastructure for low emissions infrastructure. So after the policy comes, we gradually start building this new low emissions infrastructure. And I don't care whether you think it should be solar or wind or nuclear power or just super efficiency. All those things cost a lot of money, and they build up slowly over time. But as you build up the stock of low emission light bulbs or wind power plants or whatever it is, that stock builds up slowly. And the reductions in emissions is proportional to the stock of low emitting infrastructure. But reducing emissions doesn't directly do anything for the climate, because the climate is not responding to emissions, it's responding to concentrations, the amount of CO2 in the air. And the amount of CO2 in the air is the history of emissions back over human civilization. And so you have an enormous amount of inertia. If you stop emitting CO2 today, instantly, you still see the effects for thousands of years. This is very different from the problems we've been used to. And it's the combination of the two things that's particularly dangerous. So let's say you had an environmental problem that was very uncertain, but you didn't have this inertia problem. So you had a problem of some pollutant where one expert said it could be horrible, and one expert said it might not be such a bad problem. And you said it might make sense then to say, let's wait until the scientists figure out how bad the problem is, and then we'll figure out how much we want to spend to fix it. And without inertia, that's a perfectly sensible thing to do. But it doesn't work for a thing like CO2, where you've got a steady buildup in the atmosphere, because you can't just wait to find out how bad the problem is, because there's no way to go backwards. At least short of engineering the planet, there's no way to go backwards. Once you've got the CO2 in the air, other than planetary engineering, it's in the air. It's that combination, among others, that makes this problem so difficult to handle. The very long time scales, because remember, the flip side of the very long time scale is there's not much benefit to cutting emissions any particular year. And it's that makes it so hard to politically get a consensus, to spend money now, make ourselves poor now, to make a better climate for our grandkids. So now I'm going to talk about this kind of, they have been very taboo topics. I think it's still fair to say in some ways a wacky topic, a topic about how we might engineer the climate. This is not a substitute for cutting emissions. We have to cut emissions anyway, and I'll try and say why. But it's something else we might have to do and might need to think about to manage the climate risk. And I'll tell you a little bit about what it is and why. So here's some just definitions of things. In the language people talk about climate change, you think about the human actions that change climate. That's obviously burning carbon dioxide, but it's also methane emissions from landfills, or for that matter, it's sulfur emissions from ships. Global shipping emits a huge amount of sulfur. That sulfur has a short-term effect that kills people from air pollution, and it has another short-term effect, which is it makes clouds brighter, and it reduces the amount of warming. So the International Maritime Organization is going to ban high sulfur fuels for ships, which is going to make a lot of people air cleaner. And it's actually going to increase the rate of global warming, because part of the global warming, a big part, like half, is right now hidden by the fact that a bunch of our sulfur pollution makes the clouds brighter, makes the sky brighter, and reflects away sunlight, cooling the planet. So these are human actions that change climate. That's the climate system, and these are the impacts of climate change. And the names of what we do about them are: we mitigate, that means stopping emitting; we adapt, that means dealing with the problem that comes, dealing with a changing climate; or this middle new thing, it's actually not a new thing, but this idea called geoengineering. Obviously, if you're in the natural world, you can't adapt in the same way. So there are two completely different ideas that go under the name geoengineering that have little to do with each other, but they're both called geoengineering. I want to try and distinguish them. One are these ideas to do with making the planet brighter. And so the most obvious and famous one is that we put sulfate aerosols, basically sulfur dioxide pollution, in the stratosphere to make the planet more reflective, to cool the planet. There are a bunch of other ones. I won't go into the differences between them. All of these things share the characteristics that they're fast, they're cheap, and they are imperfect, or have limited effectiveness. And I'll say a little bit about why, but there's no doubt you could do these things, and here's the reason there's no doubt. When Mount Pinatubo erupted, it put 10 million tons of sulfur in the stratosphere, and the climate got colder within a year. And it does that for all big volcanoes. Here's the lower atmosphere temperature signal, where I've marked some of the big volcanoes, and you can see the response. And we understand that reasonably well. We don't understand the details, but the basic physics of this is pretty clear. You're putting aerosols in the stratosphere that reflect away some sunlight, which from the point of view of the climate system is not that different from just turning down a knob, which makes the sun a little dimmer, and that makes the planet cooler. And if we wanted to put megatons of sulfur in the stratosphere, it wouldn't be expensive or difficult on the scale of what human civilization does. And to give you a sense of it, it would maybe cost us 1/10,000th, not 1%, but 1/10,000th of GDP to do this. So if, for example, for some reason you wanted an ice age, we could engineer an ice age for you. And this may seem like hubris, and it is hubristic, but it's also honesty about the actual level of technological power that we have. And we won't make better decisions by pretending that we don't have that power. So if we want an ice age, we can do it. So that's this set of things. Then there's this other set of things that are things we would do to remove carbon from the atmosphere. And they more or less all have the properties that they're slow and expensive, but they actually are getting at the problem more, because if the problem is CO2 in the atmosphere, this is actually getting it out. So they're not so much hiding the problem as actually dealing with it. And there's a whole bunch of them. I'll just say what a few of them are. Probably, how many of you have heard of biochar? Let's get a show of hands. It's a very hot topic these days, but not too many. Biochar is the idea that you can partially burn biomass, straw, or wood waste, and then bury the charcoal, and it'll stay in soils for thousands of years, and that is a sort of stable removal of carbon from the atmosphere. It's quite unclear how well it actually works, but it's interesting. Biomass with CCS is the idea that you can burn, say, wood or other biofuels in a power plant that captures the CO2 and puts it underground into stable geological storage. And then in the net, you've done the reverse of what we're doing with coal mining. You've taken carbon from the active biosphere and put it back into the deep geosphere. Put it underground where it's going to stay for essentially forever. So there are ways to engineer negative flows of carbon from the biosphere back underground. You can also add alkalinity. You might say, what happens? Where did that 10,000 years come from? What happens when I put carbon in the atmosphere? Where does it eventually go? The answer is, well, it warms the climate, and it speeds up the hydrological cycle. It rains more, and that greater amount of rain means there's more erosion, and that erosion means there's more weathering, and it's weathering of rocks, ultimately, that takes carbon out of the atmosphere and puts it back in carbonate rock at the bottom of the ocean. So we could accelerate that process. There's ideas about simply mining magnesium silicate rocks and grinding them up and finding ways to react them with the carbon in the air to make carbonate rocks. And then you've permanently removed the carbon from the air. Nobody has any idea how to do this in a way that's cheap or not environmentally hugely destructive, but it's in principle possible. So I'll skip over that, and I'll skip over this. What we are doing is figuring out ways to give ourselves enormously bigger levers to manage the world, for better or for worse. And I think it's important to say that we're going to learn how to make these levers longer whether or not we have an active research program aimed at geoengineering. I just want to, actually, we'll go back one slide and give you a sense of what I mean by these longer levers. So the obvious thing that people have thought about is putting sulfur in the stratosphere. And there are a bunch of good things and bad things about putting sulfur in the stratosphere just as a technical point of view, let alone all the ethics and control issues like who the heck decides and how the winners compensate the losers, because economists tend to think about that, but it rarely happens in the real world. So there are a whole host of issues about how on earth we manage this problem. But just on a technical basis for a minute, because I'm a technical inventor kind of guy, I'm going to give you some sense of stuff I've thought about that just is not necessarily that important, but it gives you a sense of the new technical ideas out there that gives you a sense of how much leverage we have and how much more leverage we might have. So let's say you wanted to make a particle that just levitates in the stratosphere and stays there as a nice reflective particle that was designed to reflect away sunlight in just the right way. Is that possible? Well, at least on a theoretical basis, yes. There is a way to make particles levitate. If you have some little particle in the upper atmosphere where one side is warm and the other side is cool, it feels a force away from the warm side because the molecules that bounce off the warm side bounce off faster. And that's physics from the 1910s. It's called photophoresis. It has a big name. And you can use this in principle to find a way to make little levitated particles that you could release in the stratosphere and they'd levitate up to the top of the stratosphere and stay there. Indeed, we already have a layer of particles at the top of the stratosphere that may partly be maintained by this process. So I and some other people have been thinking about how you'd engineer particles instead of just using sulfur that would have particular properties you wanted to more accurately engineer the climate. It all gets us a bigger leverage whether we want it or not. I'm going to skip over these ones and come back to this. So bigger leverage is interesting, but it doesn't necessarily help us. We still have the underlying fact that our economy is right now driven by access to cheap fossil energy, and we're transferring this huge amount of carbon from deep underground to the atmosphere. And we have to figure out how to deal with the problem and how to mix and match the two ways to deal with the problem. The cutting emissions way and the way we might engineer ourselves out of the problem later on. And I want to just say a few words about why anybody would ever think about this. So your first reaction on hearing that somebody's saying we're going to engineer the climate should be, ugh, why would anybody be so crazy? There's so many times we've tried to engineer our way out of problems and they've just created more problems. Shouldn't we not waste 1 minute talking about that stupid idea and instead just cut emissions? And I think it's really good that that's most people's reaction. But it doesn't quite answer the whole story. And the reason is because of that inertia of CO2 in the air. So if you actually want to have a way to have any level of confidence that you can control the climate risk, just cutting emissions isn't enough. You have to cut emissions. And I spent a lot of my time trying to convince people to cut emissions and find out ways to do it. But because of that inertia, cutting emissions is not a sufficient tool to manage the climate risk at a given level, because you can cut emissions to 0 and the CO2 stays there. So it's not right to say, forget about this nutty stuff, let's just cut emissions. Because even if we worked pretty hard cutting emissions, we might still find that we were lucky and the climate didn't change that much and everything was fine. In which case we don't have to waste our time with geoengineering. Or we might find that we had really dramatic climate change and Greenland was really melting, in which case, at that point, cutting emissions won't solve it. You need to do something else, and that something else might be deliberately cooling the planet so that Greenland didn't melt. And this isn't necessarily what you wake up in the morning and say you wanted to do. And if you were back in 1700, you might have wondered about whether we should put all that CO2 in the atmosphere in the first place by inventing industrial civilization. But we've done that, and we're here now. And so we have to deal with the problem as it actually is, not what we might wish it would be. And how it is a problem with a huge amount of CO2 in the air, and we need to find out how to manage that risk. And cutting emissions avoids us putting more CO2 in the air, but it doesn't avoid the risk. I guess one way to say it is there's some chance that we have, kind of climate catastrophe. I don't like to use that word, but think about it that way. And that chance exists even today if we cut emissions to 0. And it grows every day we put more CO2 in the atmosphere. The chance is pretty low, but it just keeps growing. And if you are serious about managing the climate risk, you need both to think about emissions and to think about how you adapt to changing climate, but also you need to think about ways you might actually engineer the climate, as unpleasant as that might seem. This is not a new idea, just like the climate problem isn't a new idea. Indeed, the more you get into this stuff, the more you think people just keep reinventing the same ideas. So this is the report that went to President Johnson in 1965, which basically says all you need to know about climate change. It was the first report to a major world leader, in this case the US president, that really laid out the case that we had a serious climate problem. At that point, they had Keeling's measurements about CO2 emissions and concentrations. They had the early climate models, and they knew we had a problem. And the only thing that report recommends doing about it is this geoengineering idea in different words. Recommends having a countervailing climatic changes need to be thoroughly explored. They were even talking about putting reflective chips on the ocean, which is a really nutty idea. One thing that tells you is that our thinking about the core climate science has been much more stable than our sort of thinking about what to do about it. So in 1965, the first thing we thought about was some technological fix. And now I think we've learned a little more to try and learn how to cut emissions before we jump to technological fixes. But I and quite a few other people now think the time has come to also think and learn something about these technological fixes. So you might say, and some economists do say, if this is so cheap, why bother cutting emissions? We should just let the CO2 concentration go up and just keep turning down the sunlight, and that's a very cheap way to deal with the problem. I think that that is really not serious. And the reason is that would take us further and further away from the current stable climate state. It is an intrinsic fact that nothing you do that cuts emissions gets you back to the same climate you started with. It can reduce the risk, but it's not the same thing as cutting emissions. And if you keep doing that, you'd see a bigger and bigger walk away from the current climate with more and more climate risk. So this is not, I think, a plausible thing to do. I think it's easy to say that that's dumb. So it's easy to say that's laughable. But it's not so easy to say the next one is laughable. So let's say we actually work really hard to cut emissions by some combination of more energy efficiency and conservation and wind power, nuclear power, what have you, and we get some international treaty and we all work together. We actually cut emissions so that concentrations actually peak late in this century at some number. And we're going down the other side. So we've actually done the job of cutting emissions, and concentrations gradually fall. So let's say we're unlucky. We're spinning that roulette wheel and we find out that Greenland is melting very fast. Do we just stand there and let it happen? Or do we say we're going to add a little bit of sulfates or whatever it's going to be to the stratosphere to cool the climate a little bit, not all the way, to minimize the risk? I don't know what the answer is, but I think that's not such an obviously laughable idea, because it might actually materially reduce the climate risk to stuff we care about, like the high Arctic. So there's an obvious sort of problem here, and that is that knowledge that this is possible makes the climate problem look less bad. And the fact the climate problem is less bad makes it harder to get a commitment to cutting emissions now. So when I'm not talking about geoengineering, which at least other than the last year or so has been most of the time, if I get a chance to talk to somebody who's a cabinet secretary or whatever it happens to be, some politician, I will say, as most other climate science people will say, I'll say, the issue isn't just about the mean amount of the expected or average amount of climate change we're going to get for a given amount of CO2 in the air. The issue is these risks of these extreme problems. And I'll say we should cut emissions as partly an insurance strategy, in the same sense as you buy fire insurance and install fire extinguisher in your house, not because you are certain it's going to burn, but because it might burn and you want to take some precautions against that event. And so we argue we should be cutting emissions because there's some real quantifiable risk that will have this really, really dramatic climate changes. And that argument is a central argument for acting to cut emissions. But if we know that we can deal, at least partly, with those worst cases by some cheap hacking the planet, then it's hard to convince people to cut emissions. And that's the reason why this topic hasn't been talked about. So this topic, geoengineering, under different names, it was only called geoengineering since the mid-70s, was talked about basically in all the climate science from the 1965 through the MIT study of man's impact on the environment in around 1970. I guess women didn't have one back then. And to the National Academy's studies in 1977 and the early 80s. And then when climate became more politically visible in the, say, 10 or 15 years ago with the IPCC, it became politically more or less unacceptable to talk about this, and it didn't become part of any of the climate research programs or of the formal assessment of the IPCC. And that was because of sort of a taboo, and the taboo was driven by this fear. And in the last year or so, that's changed, and several of us have begun to think that this taboo is dangerous. And I'll say a little bit more about why it's dangerous. And I've said we need to learn more about how these things might work or not work. Both things are important. So these are some opinions about what I think needs to be done, which is that we need some research. Because currently, because there's been a taboo, we know almost nothing that is, good quality engineering and science about geoengineering, because there's been basically no government funding. So there's a few papers people have published in their spare time. And there's an enormous amount of kind of wacky stuff in the blogosphere about all sorts of schemes to solve the problem for nothing that don't work. And very little serious work. And yet, current understanding suggests that intelligently executed climate engineering would reduce the risks. So while there's lots of arguments, if you take a bunch of climate scientists and put them in a room and say, do you actually think that it might be better to have a little sulfur in the stratosphere than not? Most of them say yes. Dan Schrag and I organized a workshop that brought together some of the key people in the climate science world with a bunch of policymakers at Harvard 2.5 years ago. And it was really stunning. That meeting ended up having a big impact. And there were a bunch of climate science people there who were kind of the core of the environmental climate science or earth science crowd. People who 10 years ago would have said it's insane to talk about this. And in the end, almost everybody said we should do some research. There are some people who said, I hate thinking about this. I wish we weren't talking about it. I wish it would go away. But yes, we should do some research. And the reason is that we have a problem, and we can't just pretend that some tools to deal with it don't exist. But let me, this is my last sort of slide. And this is a way to frame two ways to look at how we could get in trouble. So let's say that geoengineering works or doesn't work. Of course, it's not going to be that much of a dichotomy. There's going to be lots of in between. And let's say that we think it works or doesn't work. Okay, so this is what actually turns out to be true, and this is what we expect is true. So the worst case is that we think it works, and it doesn't. That's the worst case. And in some ways, the problem is that's where we've been. We've had a bunch of the sort of climate, elite scientific world, and climate is known about this topic. We just haven't talked about it publicly. And we sort of had the idea in the back of our mind that, well, this probably would work, but we've done no research on it, which means we don't really know very much, because just thinking something works isn't the same as really doing the work. And this is terrible, because if we're here, we would actually not work so hard to cut emissions, get ourselves in a worse problem, and then try this thing and it wouldn't work. So that says something about the value of information, the value of actually doing some research and finding out more. And it may turn out that we look at this harder, and it turns out that it really is a much worse idea than it looks now, and it doesn't work. Well, fine. But at least we'll know. But if we decide not to do research, we won't know anything. There's also this outcome. Let's say that actually we find that putting some reflective material in the stratosphere or making marine clouds a little whiter by putting some sea salt aerosol in more or less works. By works, I don't mean that it perfectly compensates CO2 in the air. We won't know it won't do that. But by work, I mean it in some useful way materially reduces the climate risk without hideous side effects. I'm sure there'll be some side effects, but without hideous side effects. If it's really true that in that sense it works, and we assume it doesn't work, then we've missed the chance to really provide some environmental protection. And so we're going to let impacts happen that we could have stopped. And I think that thinking about this way helps us to think about the value of knowing something about this instead of just ignorance, which is where we're at now. It's an interesting day to talk about it. It turns out that there were hearings in the House Science Committee this morning about this topic. The first full-on hearings there have ever been about this topic. It's a topic that was completely below the radar for decades. I'm one of the odd people who was interested in this a long time ago, and actually I worked on this when I lived in Missoula back 15 years ago, and but very few people did. And what broke the logjam was really Paul Crutzen, the Nobel Prize winner for ozone chemistry, who figured out the cause of the ozone hole. He wrote a kind of little op-ed suggesting that we needed to take this seriously. And he didn't actually say much new in that op-ed, but it was what mattered, as often matters, is who said it. One of the big issues about putting sulfates in the stratosphere had always been the concern about it actually accelerating ozone loss. And the fact that Paul Crutzen, who knows more about ozone loss than maybe anybody on the planet, said that it was worth thinking about sort of changed the dynamic. And now suddenly it's a relatively hot topic, but there's still not really any research. I'll say one last thing just in terms of if you want to know more. The United Kingdom Royal Society issued a full study report about geoengineering, the first one that any major sort of science academies ever issued. I was one of the co-authors of it. It just came out in September. And since that, the British government actually has announced a research program, a formal research program on geoengineering. And there's a German program as well. There's no US program yet. But that's sort of the state of play. So to wrap up, I am not saying that this substitutes for the need to cut emissions. I'm not saying that we know enough now to geoengineer the climate. But I am saying that we have a serious enough problem that we need to be serious about it. And being serious about it, among other things, means using the tools that we have to manage the risks that we have and thinking hard about the ethics and the politics and the control of those risks. There aren't any easy answers. Maybe I'll end with one last analogy that I often use, which is suppose that aliens from outer space land in some capital, maybe it's Beijing, and they give us a box that has a knob to control the global temperature, maybe another knob to control CO2 concentrations, another knob for pole to equator temperature gradient, various things about climate change, climate of the Earth. If that happened now, we might fight a war over where those knobs should be placed, because we have no international mechanism to agree about where the knob should go. Not everybody has the same answer about where they should go. Some countries will win and some countries will lose under different climate states. And I don't think aliens are going to come down and give us that box, but the scientific and technical community is going to basically deliver that box to humanity over the next couple hundred years, like it or not. Those are natural outcomes of an increasing leverage that science technology gives us over the planet. And I think my number one view is that we better start thinking and talking about how to manage the problem sooner rather than later. It's always true, whether we like it or not, it seems that technology runs faster than our sort of social ability to cope with it. That's true of cell phones and whatever the ethics should be about whether you talk on them in restaurants and any number of other things. We are confronted by very fast-moving technology, and our ethics and structures of managing and controlling that technology tend to lag behind. And I think for this, it's important we begin a conversation sooner rather than later about what it means to have the tools to engineer the planet, because we're rapidly getting those tools, like it or not. And we will make better decisions if we're forthright about what tools we actually have. Thank you very much. So I'd love to have questions. Yes?
Given that supposedly the Chinese were modifying the climate to make things nicer for the Olympics and for some of their parades and things, do you think they're already working on this sort of engineering to offset all these coal plants that we're in?
So the question was, given the Chinese are already doing weather modification, are the Chinese working on this? And so two comments. One is it turned out the Chinese weather modification was a bit of a joke. But what the Chinese really did do was they used the Olympics as a means to force through a bunch of real and sustained technological changes that have improved air quality. So they used the threat of the Olympics to force the installation of more sulfur scrubbers than the US has. We think the Chinese is lagging behind us. They have more sulfur scrubbers installed on their coal-fired power plants than we do here in the US. So don't just joke about Chinese. They are getting serious about air pollution because a lot of Chinese are dying from air pollution. But on geoengineering, I am pretty confident that they are not working on this in any way.
Yeah, in the early 90s, Edward Miller suggested that in order to combat military refracted material in the atmosphere to reflect UV rays. Shortly thereafter, the military, both the Air Force and the Navy, started spray programs using aluminum oxide and barium, both highly toxic to humans, which you'll still see happening today. No one ever mentions the airplanes. So they talk about all the stuff that rises up from the pollution from the factories and such. Watch the airplanes. Remember little contrail we watched when we were kids, we'd say, oh, there's that, I wish I was going red, going anticipated. Now you have these massive plumes from horizon to horizon that fan out and cover a perfectly blue sky within half an hour to turn it white. And those aren't being mentioned. What are these programs? Are you aware of them?
So, first of all, airplane contrails are mentioned a lot, and they're a serious problem, and there's a lot of research on them. So, it is true that airplane contrails are changing climate, but not because of some strange secret government program, just because that's what happens when airplanes fly at that altitude, and that's what they do. I think what you're referring to is something that often is called chemtrails. There's a group of people, and you may be one of them, who believes there's a really secret government program that's doing this. Understood. So I don't think any such program exists, and I'm pretty confident. Governments are not very good at keeping secrets.
Go to the U.S. Air Force website and type in
I know, and I actually, I didn't meet Teller, but I have, to full disclosure, I work with Lowell Wood on these things sometimes, who was Teller's #1 second, who, in my opinion, was a bit of a war criminal for what he did during the well, that's too strong, but what happened during the X-ray laser days. But
if you just go on the Air Force website and type in
understood. But
come up and says only the weather by 2025.
Correct. Yes, I've seen. So let me speak. So yes, I've seen this, but there's a bunch of nonsense that comes up on any sort of institution's webpage, from the University of Montana to the Air Force, and it's not necessarily connected to reality on the ground. So two things to say: if there is it just doesn't work that way. There wouldn't be a large program like that with secret, because there's just no way you keep that many people secret. No, it's not. Let's open up to some other questions. I mean, I think the bottom line is no, there is no big secret program, and the reason I'm sure about that is there basically is just no history of programs at that scale being secret for that long in this kind of society. Yep.
So you're talking a lot about these reflective materials, and I'm curious how much that would reduce sunlight and what that would do to photosynthesis, for example.
It's a great question. So the question is, how much, so if we reduce the amount of sunlight that gets down, what does that do to photosynthesis? Plants need sunlight. Does it slow them down? So the answer turns out to be that we know something about that, and the answer is not much. So if you're talking about a couple % reduction in sunlight, plants are only, most ecosystems are not sunlight limited, so that the effect is not as big as you think at the beginning. Second, there's an issue of the direct to diffuse radiation. So sunlight both comes direct beam and it comes in the scattered beam. And it turns out that plants actually in general, prefer to see scattered radiation than direct radiation. So during Pinatubo, there's pretty good evidence that net primary productivity, the rate at which the plants grew, went up, not down. So the total amount of sunlight went down, but because more of it was in the scattered rays, that allows more of the leaves that are deep in the canopy to see some sunlight, and the leaves at the top not to be so saturated, and that makes photosynthesis a little more efficient. And that's what we saw during Pinatubo. It's what you'd expect to see from what biophysiologists tell us about the way photosynthesis should work. So I think there's some good confidence that that is not a big issue. But it's not a non-issue, to be clear. If you do anything that affects the sunlight level a couple %, you're going to see ecosystem changes for sure.
Going back to the idea of carbon capture and storage, what percentage of the proposed locations are looking at utilizing biofuels instead of coal bed methane and other fossil fuels?
I don't know. I would say a fifth. A tenth. It's not a big focus, but it's something that's picked up a lot of attention recently. There are there are several in Europe that have looked at it. I mean, right now there's a whole bunch of hype around carbon capture and storage. It's very hard to tell what will actually get built. But there's certainly, it's now getting a fair amount of attention, this idea that you might want to combine biomass with carbon capture and storage to make negative emissions. So it's very hard to guess. But I would say that that idea, which seemed to be nutty 10 years ago, is now taken closer to the mainstream. Yep.
If we were to use sulfur in the atmosphere, would that combine with water and enhance our acid rain problem?
So it's a good, very obvious, good question. So the question was, if we put all this sulfur in the atmosphere, does that make acid rain worse? And the answer is yes, but essentially undetectably. So we put about 50 million tons of sulfur in the atmosphere right now, and we do it in a limited number of concentrated places like China, where we have pretty horrific impacts at those 50 million tons. In order to modify the climate, we might be able to get away with as few as a couple million tons, so 4%. But we'd be spreading it evenly. And when you work that out in terms of the impact on, say, surface water pH, and then it turns out to be a non-issue. So that's both a back-of-the-envelope calculation, but then Alan Robach did a full calculation where he actually calculated, assuming you put the sulfur in the stratosphere, how much surface pH change you get, and it's just tiny. But it's an obvious and good question.
I have two questions about carbon cycle engineering. The first is, if you were to add, say, for every ton of iron and magnesium to the oceans, how much CO2 would that take out of the atmosphere, and same thing, what would be the impacts in the oceans?
So there's two questions there. So this lady referred, first of all, to adding iron to the oceans. And adding iron to the oceans was an idea that at one point seemed to have a huge amount of leverage and possibility. Turns out there's a bunch of the ocean which is what we call iron limited, where the ecosystem in the ocean surface doesn't use all the nitrogen and phosphorus nutrients, and it appears to be limited by access to iron. That's pretty well understood now. And the idea was if you add a little bit of iron, that might help to pull carbon out of the air. And there's even some real evidence that the glacial, interglacial cycles are partly driven by this, by iron that blows off the continental shelves getting to the mid-ocean or not. So there's a natural process here. And people have the idea that very tiny amounts of iron could put a huge amount of carbon into the ocean. I think it is now pretty clear that that doesn't work by any measure. So here's two things to say about it. One is that if you remove the iron limitation over the entire ocean, which would mean messing with the ecosystem of the entire ocean, you only get 1 gigaton a year, which is 1/8 of current emissions. And so from my point of view, once you learn that, forget about it. I mean, why would I bother to mess the entire ocean up? I might consider messing the entire ocean up if that would, solve the whole problem, because then at least there'd be getting a big benefit from a big impact. But if I'm only getting 1 gigaton a year, why would I do this? And now that people have done more experiments, it doesn't even look like you get a gigaton. So it just doesn't work that well. Now, the other question, if you add these magnesium silicates to the ocean, that has very little impact, because they're just dissolved ions that basically hold CO2 in the ocean. But the problem with there is that you have to put an enormous quantity in, and we have no idea how to do that in a way that it has a reasonably low cost or doesn't have other subsidiary environmental impacts. But it's clear in principle that, in a sense, that the climate problem is about CO2 being, for those of you who are chemists, an acid gas, and it's making the oceans more acidic. And if you put more of the basic compounds in, which is what the Earth will do naturally anyway by weathering, if we can accelerate that, we more or less have literally solved the problem. But nobody has any idea how to do that.
I wanted to thank you first for coming here and discussing this with us. It really means a lot, I think, not only in just the information that you impart to us, it also keeps the momentum about discussing climate change going. So I would like to thank you.
Thank you.
As far as that goes. I'm reminded in what you're proposing, I'm reminded of the early 70s margarine commercials where it says it's not nice to fool with Mother Nature. It disturbs me on that level, because I think, as we've seen in the past, whenever we as humans try and fool with Mother Nature, we end up, as you had stated earlier, creating a lot more problems than what we solve. Some of the concerns where you're discussing about changing cloud albedos. I mean, you have a difference between low clouds and high clouds, whether your albedo is actually warming or cooling. In reducing emissions, it's not just fossil fuel emissions. I mean, we have cement production, which is a huge part of CO2.
A few percent, but
when there's many things I think about the climate cycle and its effects that we don't even understand yet. And I think at this point it's too much of a black box to really start thinking that we have, as you stated, we don't have the ability to do it right now, but even thinking that it might be a possibility for us to determine how we can change the climate when we aren't really sure yet why the climate is the way it is. I'm wondering if it's more, and I like the topics that have been brought up about China. I think it's maybe more of a concern that we should start thinking about what you're proposing, but more on the grounds of trying to prevent other countries from pursuing these courses, which might actually endanger maybe not just local weather, but climate on a global scale.
So those are several things, and they're all really good points. I guess I'm going to try and pick up on a couple of them. One is, you can think of lots of cases where we've tried to intervene in nature and blown it. And a lot of those sort of, we'll all bring our own ones to our mind, from mongoose in Hawaii to, there's a long, ugly list. But it's important to say there's actually lots of places where technological fixes have more or less fixed. Not perfectly, there's always side effects. But I mean, internal combustion engines are really noisy. And so instead of fixing the root problem, we put mufflers on them, which is a pure end-of-pipe technological solution, and actually nobody complains about it that much. And for that matter, the basic way we've handled air and water pollution in the developed world has been to put on various sorts of scrubbers that are end-of-pipe technological fixes, and none of them were perfect, and there's some side effects, but more or less we actually made the air and water quite a lot cleaner in the last while. So there are actually quite a lot of examples where we've deliberately sort of engineered a fix to a problem we already had and got better. Not solved everything, there's always some side effect, but it's, I think you can think of examples on both sides, ones that sort of worked and ones that don't. But there's no question that we have often been overconfident about how well technology would work. So the other thing you said was that we don't know much about the climate system, so how can we mess with it? And that one, I think the answer is we don't have the luxury of waiting around to know more about it. We are messing with it by putting this enormous amount of carbon in the air. And the same science that says that we've got a problem with all the carbon in the air says that if we had 1% less sunlight, we'd have less problem. And so those are linked facts. They're both uncertain, but I don't think it makes sense to say just because of the climate science uncertainty, we shouldn't think about this kind of fix, any more than it makes sense to say just because of the climate science uncertainty, we shouldn't think about cutting CO2 emissions. I think they're both kind of equally black and white and ultimately not supportable statements. I do think we have to learn our way up. I don't think we should start doing it today. Indeed, I don't think we ever necessarily have to do this. I think we have to have the ability to do it if we're serious about managing climate risk. And to pick up on the last thing you said, and I really agree, we need, say, if you want to take we being US instead of we being the world, we need the capability to manage this and to understand it, even if we never want to do it, in order to protect ourselves from other people doing it. One of the problems with this is it's so cheap that a small country could do it. Bangladesh, Libya, China. And so one of the many reasons I think we need a research program is the only way we're going to know for sure if they're doing it, and if they're doing it, tell them, if we think they're doing it incorrectly, tell them that they shouldn't be doing it, is if we know something. We won't be able to stop them or understand what's going on if we don't have some research. Chuck.
At first you had those 4 points up there of kinds of energy.
Yep.
There was nothing for hydro. Well, I know the problems with big dams and all that, but there's an enormous amount of energy in a single river. I mean, you build a dam, you get to use the force of the power of gravity once.
Yep.
Well, if you use small units all the way down the ocean, you could use the same energy to create electricity 1 million times between here and Portland. Well,
so the question was, what in my list of big things we could do about decarbonizing the electricity system, why didn't I have hydro? And the answer is that I listed things that are deployable more or less around the world at huge scale. And all these things have that character. I mean, there's some, you can't deploy each one in the same place, but they're all very widely deployable at huge scale. I think it's pretty clear that hydro is not like that. To give you some numbers, as a society globally, we now use a little more than 10 terawatts of primary power. And the very uppermost limits for the amount of hydro we produce are, you know, 1.5 terawatts or 2 terawatts, and that's if we dam everything. And the environmental impacts of doing that are almost certainly horrific. So my view, personally, on hydro is we should think about removing some of it, not adding to it. There is a view that, which is what Chuck just said, that run-of-river hydro would have less environmental impact than big hydro. And that's one of these very popular views for which you cannot find, to my knowledge, a single serious study to support it. So the question is, per unit electricity delivered, is a small dam better or worse than a big dam in terms of environmental impact? And I'm not, there's a widely held view that small dams are better per unit of electricity, and it's not clear to me that it is. I think we would really have enormous impacts if we dammed all our rivers, and the benefit in terms of electricity would be not so huge. So I'm not that keen on a lot of hydro, both because we're reaching the upper limit and because I think the impacts, environmental impacts, are big. Should I take, who's in charge? Should I take 2 or 3 more?
How about 2 more questions?
Okay.
I have 2 questions.
You only get 1.
2 quick questions.
No.
The first one is very quick.
Okay.
Does the international group of scientists to which our colleague Steve Running belongs, to what extent are they talking about this question of engineering?
Yep. So the question was, does this international group of scientists called the Intergovernmental Panel on Climate Change, which is the sort of high-level assessment body that tries to give a unified view about the climate problem, or assess the knowledge about the climate problem, what does that body have to say on this topic? And the answer is close. So I'm like Steve Running. I've also been a convening lead author or whatever in the IPCC process. And the answer is almost nothing. So there was a chapter 2 IPCC reports ago, and Greg Marland and I and Haroon Khashoggi wrote it. Now that this topic has suddenly got a lot of hype, there is a lot of talk about what happens in the next assessment report. And I think this is changing day by day. It's being negotiated. I think what's going to happen is it's going to be woven through quite a few chapters across the report, which I think is actually not going to work very well, because there won't be a single chapter that tries to bring it together and say, here's what we don't know, here's what we do know, here are the problems. So the answer is it won't be well handled.
The other one is big.
No. Privately. Let's get 1 more. Here.
So
sorry.
What's the scope and duration and cost of the research that would give you the confidence to use this?
That's the kind of question I would have got if I'd been in Congress today. I think that we could actually start with a pretty small program. So if you had just $10 million a year, which is the current just straight research budget for climate change in the US is more in the $2 billion category. So this is talking about a pretty tiny amount of money. You would actually already start to learn much more, because we've had nothing. I think, though, if we're really serious about building up the robust capability to do this, you're talking something in a category that grows to 100 million class money, because you really actually need to do some engineering as well as some climate science to begin to learn it. So that kind of magnitude. But you could start small, and I guess I'd say one more thing. There are some people now who are lobbying actively in DC for a kind of crash program on geoengineering. And I think that would be very foolish. Because, first of all, well, research programs can be killed by having too much money, too fast. Right now, there's not that many people who have thought about this seriously. There's a bunch of nonsense out there. The way the dynamics of government programs work is if you just pour a lot of money on something that's kind of ill-formed, is a bunch of the money gets wasted in nutty stuff, and then 5 years later you have congressional hearings about all the nutty stuff that happened, you shut it down. So you have to grow these things slowly from some base.
So that's the cost, but what about the confidence to use it?
Will we ever have that confidence? The answer has to be, I don't know. I mean, because this is a problem. This is back to the global governance question. Who the heck makes a decision? How do we ever make a decision? I mean, let's say we get a case where, pardon?
We're the ones who cause this problem. It's not like
individuals cause this problem.
The progression of science and technology, and like it's our desires that fuel all this.
Correct, but individuals cause these problems in the end by individual actions. But for collective problems like this, or like many other collective problems in our society, I think individual commitment and individuals help solve them. But I think we must have sort of collective action through governments to solve these problems, whether they're lead in gasoline or air pollution or what have you. There's just no way that individual actions alone are going to solve these, as important as individual action is.
Well, no more sneaking in questions.
All right.
So thanks, Lee.
Thank you.